All right, so back to science and the topic for today. So I'm going to begin with a conversation with Cumrun Vafa, and then I'll segue into your questions. We'll take your questions during that session as well. Cumrun Vafa is the Hollis Professor of Mathematics and Natural Philosophy at Harvard University. He has won so many awards that it would take half of our time to list them all. The Breakthrough Prize is certainly one of those. He's well known for tremendous ideas that have set the course of many areas of research into string theory. Again, we'll talk about some of them, but perhaps those of you who've read my books are familiar with the work that he did with Andrew Strominger, giving us the first microphysical calculation of the entropy of a certain class of black holes, which is rightly regarded as one of the real crowning achievements of string theory. So let me bring in now my friend, Professor Cumrun Vafa. So welcome, Cumrun.
Nice to see you, Brian.
Good to see you. Thanks for joining us. I know you're joining us from home at the moment, I think.
Yes.
And just to sort of get into things. So you're a professor at Harvard, and Harvard just recently announced, as many places are, that it's going fully online with its education. Have you done online perhaps in the spring? Did you do online teaching of your students?
Sabbatical leave on spring prevented me from teaching, so I haven't experienced that. I have given lectures by Zoom, but not class. It will be an interesting experience beginning this fall.
Yeah, you know, most people, in fact, this even came up at a meeting at Harvard, because you know that I'm on one of the overseers committees there, that there's a general sense that teaching via Zoom or online is always a pale reflection, a poor approximation to the experience in the classroom. But I was sort of the lone voice in that meeting, and I said, I kind of feel like the teaching can be just as good. It's different than engaging one-on-one, but you know, in small ways and large. I'll give you one small thing. I don't know about you, but I never can remember all my students' names. I really wish I could, but I can't. But in Zoom, all their names are like right there, so I can like call on Jim or call on Mary, and it actually adds a personal touch that like I can't do in the live class, because I can't actually remember. So that's sort of a minor thing.
The Zoom account.
Yeah, exactly. But yeah, I think it will be. I'd be interested to talk to you after, you know, some of your sessions to see, you know, how you're thinking about things.
Sure.
I also want to just announce to folks that you've got a new book out. It's sort of a, well, that's the wrong side of it. There we go over here. Beautiful new book, Puzzles to Unravel the Universe. And I was fortunate to receive a nice advanced copy from you, and enjoyed reading it tremendously. So just to sort of get into things, what, you know, it's a question that many authors are asked. Every book interview that I've had, often they ask, you know, what is it that drove you to write this book? So let me just start in that way. What was your motivation?
Well, part of the motivation was to try to communicate with the public about the things that excites me about science. And I felt that maybe there's room for hands-on kind of relation between the public and the science. And I thought puzzles is a way that could, it's a good vehicle to try to bring this connection a bit more hands-on experience. Instead of just reading, they will get to do something and feel what is going on really. And in fact, it's based on a course that I've been teaching, actually originally suggested by my wife, Afarin, to originate this course to kind of communicate with freshmen at Harvard. This course called Physics, Puzzles, and Math. And based on this freshman seminar, which has been going on for about 10 years now, I gradually developed more and more puzzles and tools to kind of communicate with people who are not necessarily going to be physicists, but are interested in learning about how the physics goes about, what are the basic ideas. And I thought puzzle is a fun way to get them into seeing what are these deep ideas. And you know, the puzzles don't have to be complicated to kind of illustrate some of the points. And then the nice thing is that even simple puzzles can relate to, you know, the latest things we're doing in physics, modern physics. You know, what are the latest and most interesting aspects of the fundamental physics can be connected to simple looking math puzzles. And this was both a fun way as well as educational way to bring this about. And that was through this experience from this course, I decided that it would be great to have this in the form of a book that others can also benefit, even those who are not possibly the students in my class.
Were you a puzzle solving kid? I mean, is that something that fired you up when you were young?
Yes, I love puzzles. I always loved puzzles, and I always tried to, it was always fun thinking about them, but I also had this view about things around me, which later got me interested in science, which also was a way like viewing the whole thing as a big puzzle. And, to me, from the childhood kind of questions like, why is this thing moon up there and it's not falling? And why is this and that and this way and that way? So these kind of things that are around us, even as childhood, kind of got me started thinking. And then puzzles was kind of a more simpler and more well-structured way of asking a simple question. And it was much simpler than the complexity of the reality around us, but it was a way to kind of get me started in thinking about things that I found amazing about our universe and this and that later on. But it started from my interest as a child.
Now, sometimes when people hear the word puzzle, they think in terms of, it's fun, it's a game. Sometimes when we think about the questions of the universe, we use very different language that has a more sort of gravitas, more profound quality to it. Do you find with your students that there's any tension between those different sort of levels of profundity, the gamification versus sort of the profound investigations into the nature of the world, or do they seamlessly come together?
They actually seamlessly come together, I would say, because even as physicists, even when we do research, and you well know this, of course, Brian, that when we see something gets understood, it is always in simple terms. If something is complicated, we don't feel we have understood it. So it should eventually be, the profound ideas should be so simple that, quote unquote, the kids should also be able to understand. Otherwise, we don't think we have understood it. So this simplification or understanding in simple terms is a requirement really to say we really understood something. And it's not like if you have something which is profound, it should look complex. In fact, it's the opposite. If it is complex, means you really haven't quite understood it. You have to bring it down to its bare bone, to simple terms, and only then can you really feel you have understood it.
So most puzzles that we get set by, in school or even in your book, they're made up by a human being. When we are investigating the sort of the puzzles of nature, do you feel that is ultimately a wholly human quest, that we kind of look out at the world and we puzzle about things and we frame our questions perhaps in a mathematical language, but ultimately, as you say, it's just a puzzle? Or is there some kind of deeper source for these puzzles?
It's a good question. I have thought quite a bit about the relation of puzzles, magic, and the universe and how this works. To me, the universe has this magical quality, and like puzzles, which are sometimes magical, and we try using scientific methods to try to explain this magic. And there's a difference between the regular magics and the universe as a magic. Scientific explanation of it does not make it less magical. In fact, it adds to its spell. So it's kind of a little different from regular puzzles. So it's not something like we made it up. It's kind of there, and we try to understand it with our own terms. It has a different quality of a puzzle. It's a different quality of a magic to it than regular things that we can make. Of course, we get inspired by things around us, and we try to parallel what we see around us in the universe. But I would say that it's not like something we have imposed from us to the universe, but rather we're just mirroring what we see in some form, in some obviously imperfect way, in our way, to try to model it in some form.
Right. We thought it'd be fun, since it's a book on puzzles. In a moment we'll turn to questions of string theory and space and time, but we thought it'd be kind of fun during that conversation if there's some folks out there that want to puzzle over a puzzle and see if they can come to the solution. So if you can pose one of your puzzles, and our thought was, for those of you who are out there that are interested to try to solve it, The solution should take the form of a picture that shows the solution to the puzzle. And in the chat, World Science Festival will post, I believe it's an email address or some other place, you can see it, where you can post your solution. And among those who get the right answer, we'll do like a little random draw, and you'll get a signed copy of Cumrun Vafa's new book as a prize that the festival will provide to you. So give us one puzzle that you think fits into this category of interesting things for people to ponder.
Sure. Well, one puzzle is the following. Consider 4 cities. I gave them name A, B, and C, and D, and the 4 corners of a square. So they are equally distant. I mean, the neighbor ones are equally distant. A and B and A and C are the same distance, and they form corners of a square. And the task is to find the highway system which connects all these cities. Now, the highway system that you find should have the shortest total length. It should be able to connect every city to every other city. It does not have to be a direct connection between every city and every other city. As long as you can go from any city to any other city, that is fine. And we just want to know what is the shortest highway system that connects all the cities. Of course, shortest highway system is useful because you want to spend least amount of money if you want to connect all cities. And so that's the puzzle. And what it has to do with physics and so forth, perhaps we can explain afterwards.
So the form of the solution will be someone's got to draw a highway system connecting the 4 cities, take a picture of it, send it in, and really specify the details of the directions that those various roads are taking.
Exactly. No need for proof of it. Just the drawing and the specification on the drawing is sufficient.
All right. So if anyone's still paying attention to our conversation as opposed to trying to solve the puzzle, we're gonna move on from there, and we'll come back to the solution toward the end of the discussion. So your line of research, and mine as well for a long time, has been in the area of unified theories, string theory. Of course, as many people who are listening to us well know, Einstein himself was in search of a unified theory toward his final days on planet Earth, and never really found it. For you, what's the motivation? What's the drive to find this sort of final theory, or this unified theory?
Well, I think that I enjoy it without understanding why I enjoy it, and I don't think it's an aim to find the final theory, because I don't think I will for sure not be able to succeed. I'm sure about that. I don't think it will be something achievable in our lifetimes. So it's not a precise goal as a final quest of something for me. I think it's a kind of a journey more than anything. And I feel that the thing that amazes me is that discovering something beyond us, discovering and connecting to something bigger than ourselves, discovering that there's something out there which resonates in us, and we can kind of understand pieces of it and make sense out of it, which is longer than our short lifetimes, and much, much bigger in space and validity than the tiny quote place like Earth that we live in. It's applicable to the whole universe. Understanding these laws allows us to feel a little more connected to the meaning of the whole existence in a broader term. That is really what I want. That's what gives me satisfaction. Yeah. Of course, when I try to connect things and try to see the connections, it's like seeing a piece of art or enjoying it, and just even if I'm not doing it, and if somebody else is doing it and just watching it, it's already inspiring and makes me really enjoy it. And so that is also another aspect. So it's just beauty of appreciation of what's going on is another aspect of it. Of course, being part of it and doing minor contributions here and there makes it even more fun.
Sure. So, I've asked and answered the following question like 10,000 times over the course of the last decade or so. So I'm happy to cede it over to you. Can you give us just for those who perhaps don't know, what's the basic idea of string theory? I've always wanted to ask that question. I've always answered it. I've never asked it before.
You are the expert on explaining this so beautifully. I cannot do any better than you, for sure, Brian. But I don't know what is the easy way to say what string theory is. I would say that, I would start perhaps by describing a little bit about what is the basic questions before I get to what string theory is. Of course, from old days we know gravity. From Newton's day, he understood the quantitative understanding of how gravity works, and later we learned about particles, fundamental particles, things like electrons, and when we understood electrons and how the atomic structure works, we found quantum mechanics is crucial. This was last century, beginning of last century. And so when people tried to put together Newton's theory, which was beautifully extended by geometrical idea of Einstein, when he wanted to combine that piece of physics with quantum mechanics, which described the tiny pieces of atoms, it didn't work. And it came accidentally. It was accidentally discovered by physicists trying to do something completely unrelated, that if you start talking about vibrating tiny objects instead of point particles, instead of points like tiny little like spaghetti loops, but very, very tiny, then you somehow manage to get rid of these contradictions that Einstein theory had with quantum mechanics, which describe how electrons work. So this was the emergence of the idea of string theory, basically as a way to resolve the paradoxes between Einstein's theory and quantum mechanics. So the Einstein theory, which is great in describing how things work at large distances, and quantum mechanics, which was great with short distances, got unified using this extra ingredient that fundamental objects are not points, not point particles, but extended little loops. And these vibrations of these loops give rise to different kinds of particles, and different kinds of interactions emerge from strings.
Let me just jump in right there, though. I want to ask you a question on that. Freeman Dyson, in an article that I read in the New York Review of Books, but I think he's had said it in different locations as well, he questioned whether we should ever even worry about the contradictions between general relativity and quantum mechanics. He said there's no reason to worry about that. They're just describing distinct realms of reality, and the contradictions are arising because you don't want those realms to be described in the same language. Does that hold any water for you?
Well, I'm not sure exactly what you might refer to, because we already know that there are many pieces of science which emerge from contradictions. In some sense, we welcome contradictions, because contradictions point towards something we don't understand, and potential resolution of that leads to new ideas. However, there's one sense in which I can perhaps understand what he may have meant, and that is in the context of what we call duality in string theory. So occasionally we come up with two completely different pictures which look contradictory, contradicting each other in some way, but this contradiction gets resolved by viewing it in a very novel way. So it's kind of like a different viewpoint. So you have two different things which look like there's some inconsistency, but there is not. Of course, trying to figure out why it's not is the key. It is the key to understanding what is going on. So the apparent contradictions are there, but not the real contradiction. And I think maybe that's what he's referring to. So we shouldn't be bothered by apparent contradictions, but we should perhaps welcome them as an opportunity to get to understanding deeper reality behind why they are the same, or why there are no contradictions at all.
Yeah, no, certainly. I mean, you think about special relativity emerging the contradictions between electromagnetic theory and Newtonian mechanics. You can think about quantum mechanics emerging as a contradiction between observational data of certain particular systems and the classical description of those systems. So I totally agree that contradictions have been the most fruitful things that we physicists have encountered. I think what Freeman Dyson was referring to, he didn't believe that gravitons exist. He didn't think that gravity would ever need to be quantized. I'm not exactly sure how he justified that thinking, because I mean, we'll talk about it in a minute, but when you think about things like black holes or the Big Bang, it seems quite clear that to gain the full understanding, you need to put general relativity together with quantum mechanics, because there's extreme realms of gravity and tiny realms of space, and it's very hard to imagine a description that wouldn't unite them. But I guess he was thinking that we would one day just have distinct descriptions that would never require gravity and quantum mechanics to talk to each other. Again, it's hard for me to understand where he justified that thinking, and I gather it's hard for you to see it as well.
Yes, I think I think that the quest we have in science is unification of ideas. To us, having different rounds which have nothing to do with each other and describe reality is not a happy ending for understanding what is the ultimate goal, or how do the things relate. It's kind of giving up.
Yeah.
I don't think I will subscribe with that to that viewpoint. But of course, we have understood much more, I think, especially in recent times, about connections. You mentioned black holes. And for example, fundamental things that we mentioned, electrons. You might think, what does an electron, fundamental entity, this tiny thing, have to do this massive singularity in space, which now have a picture of, luckily, the black hole? How could they have anything to do with each other? And now we have learned via string theory that they are related. And the simplest relation to explain is that we have learned the following fact is from string theory, that gravity is always, no matter what kind of universe you might imagine, is always the weakest force. So, for example, the electron has a repulsion. If you have two electrons, they have a repulsion, electric repulsion force, which is much stronger than their gravitational attraction by a factor of 10 to the power of 40 or something. So it's a huge difference between these forces. Gravity is always the weakest force. The electrons really strongly repel compared to the tiny attractive force they feel. And the question is why? And we learned that this has to do with the properties of black holes. So understanding black hole, that thing which has nothing to do a priori with this tiny little electron, gets to explain the fact that gravity is always the weakest force. So these kind of connections come from quantum aspects of gravity and gravitons existing and all that, which are crucial in hanging the whole thing together. So these elementary excitations like electrons or gravitons, and these big excitations like big black hole are actually intimately, deeply related. And we have seen many examples of that by now in string theory.
Yeah. A number of the chat comments, I'm just quickly looking at them, by a number of the listeners like Raju Radhi, and one listener whose name indicates the question at hand. Their name is Loop Quantum Gravity. So a natural question is, so string theory is an approach to putting general relativity and quantum mechanics together. There are other approaches that have been put forward. What do you think about loop quantum gravity?
I think no approach is on par with the amount we understand in string theory. So I think it's fair to say that the other approaches are attempts, and many of them, there are not too many attempts, but none of them are as developed as in context of string theory. And perhaps there's some connections that we may discover between some pieces of these ideas within string theory, but I would say that they are not on par with string theory.
Right. Yeah, I hold a similar view, but I think we're both perhaps biased. The other community might have said the same thing in reverse, but let them have their own discussion if they want to.
Yes, we're in different chat here.
Yeah, exactly. So, when I was a graduate student back in the 80s, which is more or less the time when you were. When did you get your degree?
1980.
I got my 86. Yeah, so around the same time. There was a general sense that we both can recall that some people were saying, okay, the end of physics is near, right? We have this new theory. It's just going to unify gravity and quantum mechanics together, give us the final description of everything. And at that time, the older physicists, I think, knew well that this was over exuberance. That I remember talking to Ed Witten at the time, and he was like, "This is extremely exciting," but he was like, slow it down a little bit in your expectation for where this is going to go. Now we are, say, 35 years later. What's your view in terms of how far string theory has gotten? I mean, if you were to grade string theory, what grade would you give it?
Well, string theory is like opening a room which is totally dark and beginning to shine light on pieces of it. And you don't know how deep or how complicated, what shapes you're going to find. So I can easily see that with 35 years ago or so, we might have thought, the room is tiny, one flashlight, the whole thing is done. We get the all aspects ready and understood and ready to go. But of course, if you don't know if it's a tiny room or it might be actually a big tunnel or it could be completely complicated. So I think it's hard to give it a grade because it's we don't still know what is the totality of this thing that we are calling string theory. It's like really walking and, shedding light on this piece and that piece and saying, oh, no, this is not just a little room, it's actually a big cave or this big this and that. So we're beginning to get pieces of it understood. And so it's going to take a while for us to really delve into all aspects of string theory. What I would say is that we have discovered so many little corners in that room that are so exciting. Each little thing is like a gem. And we have, we said, wow, look at this little thing here. Isn't it cool? Let's try to understand what it means about the rest of physics. And we get absorbed this for a few years and say, oh, no, there's this other gem over there and so forth. So it's like a kid walking around in this candy store and discovering this and that and so forth and putting all together. And you might ask, okay, so are you done with this candy store? No, we're still continuing our journey in this way. And what grade I can give, I would say we have found so many exciting stuff in string theory that it's you could give a grade of A+. But if you ask, have you been able to connect to any single experimental result that you can actually explain using your theory, the grade is not A for sure. We have not been able to do that. So therefore, depends on what is the exact aim. And we can only be modest in that we can continue this journey, understand pieces of it. We have connected many different aspects of physics together. We have understood how quantum theory and gravity can be consistent. We have seen how gravity could be related to a manifestation of forces like electromagnetic forces or generalizations of it. We have seen how dualities work, how something which looks one way could be completely related to completely different things. So these kind of different aspects have shed huge light about what we understand. We have learned so much more about black holes. We have learned many, many things. And of course, the longer this journey is, perhaps the more we're going to learn more new, exciting things. So therefore, maybe we shouldn't aim to have a short journey. So the longer journey may not be so bad. But of course, it would be nice to get a few experiments on the way as we walk on this journey.
Well, some string theorists have said, I wonder what your view is, they point to the developments that began in the late 1990s that showed a very deep and unexpected link between string theory and the more traditional way that physics has been able to describe elementary particles, namely quantum field theory. And the deep connection between string theory and quantum field theory, some string theorists that I've spoken to take the position that the experimental program of testing string theory needs to be seen in a different light. They would say, hey, once you find this deep connection between string theory and quantum field theory, well, quantum field theory, you already know that certain quantum field theories are spectacularly good at describing real world physics. And once you have the link between string theory and quantum field theory, then in some sense, the experimental program isn't as crucial as you perhaps once thought it was. What's your view of that?
I would not agree with that. First of all, we would need to say that some kind of gravity theory is consistent with our understanding of string theory, and therefore let's not worry about the details of our universe. That's basically not giving up on interesting things that could be related to the universe we live in, or universes that could be possibly consistent and perhaps even reachable from our universe. So I would say that saying that something is consistent unless then not delve any further is basically again giving up. So I would say that to say that gravity might be related to other forces is of course great. String theory unifies them, but we would like to know more. We would like to understand what aspects of our universe is related to the consistency of gravity with these other forces. Can we make further predictions? Are there other kind of particles that there should be there? Can we learn anything about dark matter? Can we learn anything about dark energy from the string theory perspective? We know that there's this non-vanishing energy permeating the whole space. What does it have to do with Einstein's theory of gravity? What does it have to do with the fundamental forces? Are there any relations between them? Can we make a prediction about the fate of the universe? All these exciting questions that we need to understand, and I think they're extremely exciting to understand for our universe and understanding what predictions we have about the universe that we live in, rather than some hypothetical possible universe that we don't even know whether it's relevant for our universe. So understanding more specific things about our universe is something that we still lack in our understanding of string theory.
So do you consider string theory, say, to be falsifiable?
String theory is falsifiable in many ways, but to make it very falsifiable, you have to have a very specific universe in mind. So, for example, I would say that if you just would be an aspect of falsifiability. Suppose you have an accelerator which can produce energies which are 10 to the power of 20, let's say, higher than the energy of a proton. Suppose you go to that high in energy, which is, if you can arrange such a huge amount of energy, then if you don't see any evidence for extended objects of one form or another, I would say that falsifies the theory. So there is a prediction that you have to be able to see something coming up there. Of course, that's very far from the realm of experiments we can do today, by many, many orders of magnitude in energy, or even the Large Hadron Collider is a very tiny energy compared to the energy we need to reach to falsify string theory. So falsifiability of the string theory is, at this technologically, we are not at the point where we can actually do it now, but I mean, at least theoretically, we could see it falsified. Of course, otherwise it won't be a piece of science.
Sure. You know, when I look back on the papers that I've written in my career, I'd say that, I don't know, 90% of them rely on something called supersymmetry in one way or another. And many of us who have the same perspective as you, that in principle you can test string theory. If you have a big enough accelerator, you can actually, in principle, try to detect the extended nature of a string. And as you say, if you don't see it, then that would be pretty good evidence against it. If you do see it, that'd be pretty good evidence for it. But of course, we don't have those machines. We have to deal with what we have. And many of us thought that supersymmetry, this quality of nature, that for every known particle, there'd be a partner particle. Many of us almost took it as a foregone conclusion that the Large Hadron Collider would discover these super partner particles and that way confirm supersymmetry. It didn't happen, or at least it hasn't happened. Did you find that disappointing? What's your reaction?
Certainly disappointing, but I wouldn't say that we were predicting it necessarily. I mean, so let me say that. So just like you, I actually was hoping that we would see some evidence for supersymmetry in the Large Hadron Collider, but evidence was against it, and in the sense that the amount of things that we saw from other experiments did not point towards being able to see supersymmetry. In string theory, we believe supersymmetry, this amazing symmetry between different kinds of particles, bosons versus fermions, should be true at some energy scale in string theory. That energy scale has to be something that is measurable in some sense, but may not be at the low energy that we can probe in the Large Hadron Collider. It could be all the way up to the energies which we call the Planck energy, this huge energy this is the ultimate energy that we can reach. So it could be that you need to get so high an energy to see the evidence for supersymmetry. We were hoping, who knows, maybe we are lucky and, that you could see it at low energy and then we'll be happy. We didn't see it, but I wouldn't say that dismayed me in terms of believing in string theory, let's say, or to say that it had to be seen. No, we were just hoping that if it is there, then maybe we can get more insight into the inner workings of string theory and how it connects to our universe. So it's disappointment in that sense. I wouldn't say it's a theoretical disappointment. It's just like circumstantial disappointment of the universe we live in, which does not have supersymmetry realized at such a low energy. Of course, it's not still over. They could, it's still the Large Hadron Collider experiment is still going on, and they could have some evidences for that, but it's getting, I would say, as you say, less likely, and I wouldn't bet on it as I would say it's less likely even than before the experiment. But I would say that does not change my view about string theory.
So turning away from, say, the experimental side of things, which, as we've indicated, is less successful, but not necessarily a black mark against string theory, and turning towards some of the great successes. So your own work on black holes, an enormous success. More recently, there's also been a tremendous amount of activity trying to understand the true nature of space and time in quantum mechanical theory of gravity, within string theory. Have you been impressed by those developments? Any thoughts on where you think the promising avenues of research are in trying to understand a question like that?
Well, there are aspects of trying to understand deeper questions about black holes. How does it, for example, if you throw something to the black hole, after the black hole evaporates and goes away by Hawking radiation, what happens to the information of the things that you sent in? That was one of the puzzles that we expect the answer to be a way to resolve it and to get the information out. But it wasn't clear, and it still is not, to be honest, it's not clear how does the information come out. So there are some simpler models in which how the information may come out can be understood in those cases. So lower dimensional examples, there's some toy models which do that. So there's some progress in that. I wouldn't say that this is a case where I would say that we have made a big breakthrough in really understanding the big issue of black hole, but there are incremental steps in that direction. I would say there are many other directions in string theory which are, I would say, still ongoing. And it's actually one of them, which I personally am interested, relates to the supersymmetry again, which we already mentioned. So, in fact, I would turn it around. The fact that we didn't discover supersymmetry, and the fact that our universe does not enjoy this amazing symmetry between bosons and fermions, the supersymmetry, is telling us something about our universe which is deep. And that deep fact is the following. In string theory, we have two types of universes that can exist. The universes that can last forever, and the universes that are temporary, that will decay away. And of course, we would like to know which one of these two universes we live in. It turns out all the universes that we know of in string theory that last forever enjoy supersymmetry. An unbroken version of the supersymmetry should be realized. In our universe, at least in the low energy, it's not realized, which implies we do not live in a universe which will last forever. Therefore, our universe is going to be going away. It's going to decay away. So that's a fundamental lesson that lack of supersymmetry is teaching us. Our universe is not going to last forever. So therefore, the next question would be, what is the fate of our universe? When is it going to go away? How is it going to go away? So all these questions are exciting. And so this is just leading us to the deeper question about the nature. So I think these kinds of questions I find among the most amazing questions in string theory that can actually teach us something concrete about our universe. Those are the kind of questions I find most exciting, and I'm working on those kind of questions myself.
I remember the first time you told me about those results. I don't know if you recall. We just happened to run into each other in a cafe in Cambridge, Massachusetts.
Yes.
And it's funny because I was in the midst of finishing my own recent book, Until the End of Time, which has to do with possible, well, part of the book is possible endings of the universe. So I remember you told me about that way of thinking about things, and it certainly made it into a book as an endnote. I wasn't able to work it into the main text itself. But yes, I mean, thinking about the ultimate fate of the universe and to have any theory that can give you insight into questions of that sort is of course inspiring. Again, for those of you who are just joining us, I'm speaking with Cumrun Vafa. This is his new book over here, Puzzles to Unravel the Universe. Those of you who are here early on, note that Cumrun posed a puzzle early on, and in about 10 or 15 minutes, he'll describe the solution to that puzzle. But those of you who want to try to still solve it, feel free to write down your solution for the most efficient highway network between 4 cities that are at all the corners of a square. So what highway system would you use if you were charged with doing it for the least amount of money, and your highway system, the cost is proportional to the linear length of the highway itself? So back to questions of string theory and cosmology and unified theories.
But one thing before we get to that one relates to puzzle.
Yep.
I'm going to give you another puzzle as well, but this puzzle I'm going to give the solution to.
Okay.
Just without, so it's not part of that one, but I think it's interesting because it also illustrates a point about what does puzzle have to do with physics.
Yeah.
Simple way. So this is the puzzle. Can something be falling and not hitting the ground? That's the puzzle. What is falling? What could be falling and not hitting the ground ever?
Yeah.
Now, this sounds
You're asking me that question, or
no. I don't answer by you. I'm sure you can say it immediately, but this is a puzzle. This is a puzzle that you would think, okay, something is falling and it's not hitting the ground. What could it be? What does it mean?
Yeah.
And so this sounds like, it can be some kind of a word puzzle. It's not. It's actual puzzle, and it's a puzzle that Newton solved. Newton solved in the following way. So this is a question that you could raise, is that there's a moon. And first of all, the question is, why isn't the moon falling? And the second question is that, okay, if it's falling, then why is it not hitting the Earth? So those were the questions. Those were the questions. And the answer that Newton gave was so elegant, which is the solution to this puzzle. So Newton should get a prize for that, is that no, actually, moon is falling, but it just avoids hitting the Earth. Now, how does that work? And this is beautifully illustrated in his book, Principia Mathematica, which shows that if there's no Earth, if you get rid of the Earth, and if you look at the moon, and if the moon is moving in some direction, it will continue going straight. But if you had an Earth, instead of going straight, if you have anything going straight, if you have, like, for example, a cannonball shooting going straight, if you have an Earth, it will fall on it. So if you have an Earth, and if you have a cannonball shooting from it, it will fall somewhere on the Earth. If you shoot at the cannonball with a higher speed, it will go farther down and farther and farther. It can go from the North Pole, let's say, all the way onto South Pole of the Earth if you give it enough kick. But if you really give it a huge kick, it will go all the way around and it will continue going around. So what's happening is that ball is falling down, because if it wasn't for the Earth, it would go straight. So having the Earth causes that cannonball to try to hit the ground. It's falling. Namely, instead of going straight, it's falling. Just going not straight, falling towards the Earth. But since the Earth is round, it keeps on hitting the Earth. So the cannonball or the moon itself is the answer to the puzzle. That is falling. If it wasn't for the Earth, it would go straight. So it is falling, but it's not hitting the Earth because the Earth is round. So it's like a game between the roundness of this Earth and this falling of this moon. So this is an example where the puzzle and the poetry and physics all melt together. And of course, they can be beautifully explained by mathematical formula that Newton discovered. But the whole thing is a simple looking puzzle that it kind of illustrates the basic link between physics and puzzles.
Yeah, it's a beautiful example. And it's perhaps worth noting that there was a period of time when you and I and a few other of our friends would find ourselves at the same Christmas party every year. And Tracy and my wife, your wife, would all leave us because we'd all start to talk about these puzzles in one little corner of the room. And they're off, drinking and partying and having a good time. And there's one that you told me, one Christmas party, that was the following. I'll just ask it to the audience. And again, it's one that people can try to solve, which is you have a picture and you want to hang the picture, but you're going to hang the picture from two nails, not from one nail, such that it's completely stable if both nails are secured to the wall. But if you remove one nail or the other and you just leave the other in the wall, the picture will fall. And it's for those of you who are more mathematically inclined, this puzzle gives you insight into a subject of mathematics called homotopy. And it has to do with non-abelian homotopy groups and the non-abelian nature of the homotopy group of the plane punctured at 2 points. So for those of you who speak mathematical language, that's what this is about. So again, the puzzle that Cumrun gave is a beautiful one that puts the poetry of physics and motion in the universe together. And here's one, again, that Cumrun gave me that I went home. After that party, we got home at like 2 o'clock in the morning. At 6 o'clock in the morning, I was up, and my little daughter, who was like 5 at the time, we did it. We took a picture, we put it up, and I
remember getting that picture. Yes, absolutely.
Yeah, exactly. So
you gave me some good puzzles. In fact, some of them in my book about the glasses and the symmetry breaking, which is part of that book. So yes, we have had good fun with puzzles and the relation between physics and them.
Absolutely. So I want to turn to one other thing that's in your book, which was quite unusual. And for me, quite inspiring, which is you have a section on science and religion. And it's interesting, at the World Science Festival, which is what this program is part of, on various occasions, we've had programs on science and religion. And we do them because we find it a fascinating conversation between various distinct ways of looking at the world. We also have conversations between artists and scientists, artists and theologians and philosophers. So we like science to reach out to the world more broadly. But I have to tell you, there were a number of scientists who came back at us really hard, really angry that we were having a program on science and religion at the World Science Festival. They said, "What in the world does religion have any role there?" And basically, our answer, and Tracy Day, who's a co-founder with me at the festival, our view was, "What are you afraid of?" I mean, any conversation that's rich, that allows scientific ideas to be in dialogue with other qualities and perspectives on the world, is a good thing. It's not something to shun, but nevertheless, there can be a recoiling. And so, were you concerned about having science and religion? Like what led you to include that section in your book?
Well, I think that religion and science have many commonalities. So I think that the deeper truth is what one is after. And so of course, as described in the book, I think they are ultimately different realms of experience, religious experience and scientific experience, and I kind of describe them in different ways. And I wanted to share that scientists are also have views on this, and I gave examples, Newton, how religious he was, and some more recent ones, how they viewed, for example, Einstein, how did he view religion and so forth. Not so much as to try to come to a conclusion really about what is the meaning of, what should we do about religion, what should we do about science and so on, but to say this interplay between the two. And I view, in fact, more broadly what you just mentioned about the role of religion and how scientists view. In fact, even more broadly, I feel that there's this anti-philosophical bend, in which I would say religion is an example of that same thing among scientists, that somehow the scientists feel that this kind of thing is bad for science. And I think that's, as you just said, and I completely agree, a little bit of immaturity not to be able to describe and discuss it and learn from aspects of it. I think this attitude that, we know it all, and it's kind of like everything else which can be not formulated in this scientific form is a waste of my time and so on. I think that attitude is a little bit, I think, short-sighted. And I think the human experience is much wider, and I think we should benefit from it. We should incorporate it. We should not be antagonistic. We should be welcoming and try to understand it. And if there are pieces we can say something, science sheds light on some aspect, we should. And vice versa. If there's some shortfalls about the scientific methodology, we should bring in other aspects. And so I think we should be open, and I don't feel that we should be worried about the dialogue between different domains of human thought or experience.
So in your book, you do, as you mentioned, you go through in some very nice sections, Einstein and religion, Hawking and religion, Feynman and religion. What I didn't see there was Vafa and religion. If you were to have included a section of that, what would it have said?
It wouldn't have said much. It would be empty blank page. I think that I want to leave that to the. It's a personal. I view that as a personal feeling about what it is. I think the part of the problem is that the word religion is not definable, and you might say X, and somebody might think what you mean by X is a Y, and somebody might think it's a Z, and so forth. And you might say something about X, and they might misinterpret you about it as if you're saying something about Y, and there will be complete misunderstanding. So I think anything I would have said, I felt it would have to be so qualified, it would not be possible to explain. So I rather, in fact, generally not share my specific view because it's not possible to say it accurately enough. But I would say that the view that religion is in conflict with science, or science is in conflict with religion, I don't buy that in general. So I think that there's more harmony in religion and science, not any specific religion or a specific science. I think in general, the modality of humans thinking is not inconsistent with different views. Of course, you can take a narrow view of one thing and then you get contradictions. But broadly interpreted, they are not contradictory. And an example is this Lamott getting motivated by religion, by the experience about how the universe could have come from a tiny, small, little primordial thing, which was ultimately led to the Big Bang theory that he was advocating, even though Einstein was against it, and he thought this is kind of mythology, of maybe religious mythology of some kind. So these kind of views that other perspectives brings, we should welcome. We should not necessarily be antagonistic towards. And my view is, let's be open. That's my bottom line, is to be open about this.
So there's a lot of resonance between what you're saying and my own views. And sometimes when I discuss this in a public forum, some have come back at me and said, well, you know, you have the luxury of saying things like that because you live in a country that, by and large, has certain kinds of, not completely. I mean, you know, there's also said that, you know, can a presidential candidate succeed if they're willing, for instance, to say that they're not religious, that they don't believe in God? I mean, that issue has never really been fully tested. But putting that to the side, you are in a unique position, right? Because you come from Iran. When did you leave Iran? What year?
Well, I came from Iran just before my high school in 1977.
So if you hadn't left Iran, do you think that your views would still be the same as what you just described?
Yes, I still go back to Iran. Incidentally, I visit Iran. I give lectures there on physics. I love visiting Iran. They're very much interested in science. Beautiful, universities and educational centers and so on. So there's I mean, one of the things I find about science is that it's borderless. Really, it doesn't matter where you are, what time you live, and so it's a borderless and timeless adventure in a way. And I view me as an example. I don't feel like my being Iranian or American now, or both Iranian and American, has any impact about my view about science. I could have been there. I could have been here. It's just I happen to be in the US working here, but I find this borderless adventure of science is what's universal. And I think it would be great to use science as a vehicle to go between different cultures instead of clashing, instead of confronting. So I think that science in general, for me, is a gluing between different cultures, different domains of human experience, like religion, like philosophy, like art, like poetry. All these things can be glued together via science rather than science being as differentiating and saying this is right, that's wrong, this is that, and so forth. So I think in a way, I find science as a refuge in terms of the craziness that we see around us, in terms of all these conflicts that we see around us, and culturally or otherwise. So I think I don't see any contradiction, and I feel science can bring things together rather than differentiate them.
No, I totally agree. In fact, I got a letter. I've mentioned this in other settings, but it brings to mind what you just mentioned. I got a letter years ago from an American soldier who was in Iraq in the craziness of everything that was happening there. And he wrote me that he had a copy of one of my books and that it gave him the refuge that you're talking about. He could sort of shut off the bombs and all the death that was around him and all the fighting and the strife, and just enter into quantum mechanics or enter into relativity. And it felt like a universal glue, to use the language that you're using, that just allowed him to cope with the difficult situation that he was thrust into by virtue of the problems that beset the world. So one final area before we get to the solution to the puzzle. I know that the question of time is one that's very close to your heart, close to the heart of many physicists. What is it? Where does it come from? Is it fundamental? Where do you think we are on that journey to try to understand the true nature of time?
Well, it's a very difficult and important question, of course. And we don't have a deep understanding even of space, which is in some sense simpler. So I think that understanding what space really is, we have learned at least enough about the nature of space in string theory to know that there is no universal answer. That is, different corners of standing string theory lead us to different pictures of what is space, and these are what we call duality corners. One corner and the other corner, they're compatible. Different descriptions of what really space is. They look in contradiction. They cannot be possibly both be true, but they're both true. And we have learned not to say what is the right viewpoint. That is, we have learned that for the notion that what is the best viewpoint is not a good question. That question of what is the best viewpoint depends on the question being asked. And so, for example, what is space? We learned that is not a good question, because what is space ends up having good answer here or a good answer here, which look contradictory. So we have learned that much about space, which is, I would say, much easier question than the harder question and more interesting question that you're posing, which is what is time? So for time, we don't even have those corners as well navigated as space. But I would expect we will have the same kind of things emerging for understanding time. The time will not be a unique answer of what is time. It will be different, like snapshots, pictures. And for one question, that's a good answer. For the other one, the other snapshot is a better one. We're going to have these pictures next to each other, and with the totality of all these pictures, we'll get a feeling about what is time. Not for a single one of them, not for one or two of them, but the totality. That's what physics is being driven towards. That's what string theory we have learned from, the notion of duality and the fact that this fabric of different kinds of pictures come together, and there's not a one thing that is the right thing, but the totality is what explains it.
So for space, the recent results that link together the spatial fabric and quantum entanglement, is that a direction that you think is going to continue to be a promising one going forward?
That's certainly one direction that has been explored recently and has good results about it. I would say that is, among other things, that's one of the corners that I was alluding to. There are different corners that are interesting. So I would say each corner has to be explored. Not that any one corner is the answer. I'm not expecting the answer, that this is the answer. I'm expecting more a totality of the experience that string theory is teaching us, which is this duality picture that all of them are perfectly fine. Depends on what question you want to ask. If you want to ask question A, that's the best way of looking at it. If you ask question B, you go the other way. So yes, the entanglement and how the space and degrees of freedom about individual bits of information, how did that come to describe the geometry of space and so on, and how they are entangled, is certainly an example of one of these corners.
Right. So let's now turn to the solution to the puzzle that we gave at the beginning of the discussion. So maybe just quickly, because there are many more people with us now than were at the start. So maybe just reacquaint us with the nature of the puzzle, and now you're going to give us the solution.
Yeah, so we have 4 towns, 4 cities, A, B, C, and D, on the 4 corners of a square. And the puzzle is to find the shortest highway system which connects all cities together. And the highway system does not have to directly connect any city to any other city. As long as you can get from one to the other to this highway system, that would be sufficient. So that's the puzzle.
All right. And what's the solution?
The solution is, the naive solution, one might think, is, let's go to the next slide, this one, right? The most naive solution is that, well, you just go like X. Now, before we go to the next slide, I would like to say, why would we even guess the solution? Well, because it's symmetric, right? You start with a square, and so the X is one of the most symmetric ones, and it gets you from any place to any other place you want to get. So that seems like the answer. So what is guiding us is the symmetry. The symmetry of the square is guiding us towards this solution. Or we might think there might be another symmetric solution, which is the next one, which is this one. This is also symmetric. You know, you have 4 towns, 4 cities, you can have the whole edges. That would be another possible symmetric solution. So you say either this or that. And then you begin to think, you say, wait a second, it cannot be this one, because if it's this one, you can delete one of the roads, and you still can get from any city to any other. So that's shorter. And you say, in fact, you can put that city A, B, the road can go from any other place, like the middle. So you might say, well, that looks the same length, but actually you can pull the road a little inwards, and you can pull it a little inwards to be like that, with making an angle 120 degrees. And this turns out to be the shortest. And this is surprising. This is confusing, because you start with a problem which is symmetric. The 4 cities on the corners of a square enjoy the symmetries of the square, like 90-degree rotation, but this highway system does not enjoy the symmetry. In other words, to get from city A to city C is a shorter path than getting from city A to city B, even though city A and city B and city A and city C have the same distance relative to each other. So that's a puzzle. So why is it that the solution does not enjoy the original symmetry? This fact we call in physics spontaneous symmetry breaking. And this underlies a lot of amazing phenomena around us in the universe. Spontaneous symmetry breaking is a key to understanding many things. And in fact, the ideas go farther back, much longer history than we think. We originally thought we discovered this idea in the past century, the physicists, but actually it goes farther back to the Greek philosophers. So early Greek philosophers they were very smart. They had already discovered that the Earth is round, and they thought, it's at the center of the universe, and it's not moving. So these are their observations was this. And so they were a bit puzzled why it's not moving. So they had to come up with an explanation of why it's not moving, and they tried to use symmetry. So this is how they reasoned. Go to the next slide. We see this is the picture of the Earth. And they said, well, okay, suppose it moves. If it moves in some direction, let's say some direction, let's move it to the next slide. It goes somewhere, it breaks the symmetry. So it cannot move because it doesn't want to break the symmetry. So they explained that the Earth is at the center of the universe and it's not moving because if it were to move in any direction, it picks out the direction, and the very nature of picking a direction breaks this spherical symmetry around the Earth. So it's not allowed. So one of them said, this is a proof. Earth is not going to move. And then Aristotle didn't like their argument. He said, no, not a good argument. Why is not a good argument? They asked. He reasoned as follows. He said, well, suppose you put a person at the center of a circle and you put loaves of bread around that person, symmetrically located on a circle. Now, the person is at the center of the circle, and you ask them whether or not that person is going to move. Well, you would say, no, it's not going to move because at the center of the circle, it breaks the symmetry, the circular symmetry, if it were to move. Of course, that's not the answer. After a while, the person feels so hungry, person will move in some direction to get that loaf of bread. So therefore, the person breaks the circular symmetry because that's not an optimal place to be in. Being near the bread and eating it is much more optimal. So they say, who cares about the symmetry? I'm going to get my bread. I'll break the symmetry. That's exactly what happened with that highway system. The shorter highway system breaks the symmetry, and that's what the highway system chooses to do. So it's broken symmetry. Now, what does it have to do with physics, you might ask? Well, first of all, I would say that spontaneous symmetry breaking is imprinted on our bodies. You see, we live on the Earth, which basically has a 360-degree rotation symmetry around us, generally speaking. So you would think that our body should also enjoy a 360-degree rotational symmetry. Like we should have our eyes all over a circle around, rather than just in the front. But we only have it in front. You might ask why? Why do we have our eyes only in the front and not all over the circle, which would be more symmetrical? So somehow our body has broken the symmetry of circular 360-degree rotation, and it's only in one direction. Why is that? Well, the answer is Aristotle's answer, for the same reason. You want to see where the food is to go towards it. In other words, the motion to go from one place to another is optimal in a given direction, and you don't need the 360 degrees. So with all the availability of evolutionary system of how the body is designed, it says it makes sense at much more better uses of resources to just put the eyes in the front, because that's really where you want to go anyhow. So the symmetry is broken because you need to get to the food. And more details related to more aspects of modern physics, this was the discovery of what's called the Higgs particle, or the God particle, or what is the origin of the mass, is exactly the same circle that Aristotle drew, it turns out. Surprisingly, a few thousand years ago, he already had the same picture that we now draw in our books or in papers, talking about how particles get their mass. Namely, if you think about the potential that is around us, it looks like a valley. It looks like a hill and a valley, and the top of this hill area is the most symmetric point. That person is standing is the most symmetric point, but it's not an optimal point. And it turns out that the optimal point, of course, will be down on the valley area. And if you go down in that valley area, it turns out that there will be a mass related to how far away you are from the symmetric point. So the being away from symmetry translates to giving mass. So breaking symmetry means picking up mass. So this picture about how we have the eye, how we get the mass, all are related into this, and they're woven into this simple idea of this puzzle about the square.
So the Higgs gets hungry. The Higgs field gets hungry and goes for the bread on the rim of the valley.
It's hungry. It reflects our hunger, and that's why we become massive.
That's good.
In fact, Abdul Salam said nicely that the one of the fields in his model ate another field and became massive. That's called Higgs particle gets its mass that way. This is literally this picture.
That's fantastic. Well, that's great. So thanks for that mini discourse on connecting a puzzle with real stuff in the world around us. Those of you who were able to solve that puzzle, I don't know how many it is, but maybe World Science Festival people will let me know. I don't know if it was.
They have written already. We have a winner from the audience.
Winner. Wow.
So from the chat, I see we have a winner, Prayog Dash.
Is that right? He's a regular in these gatherings. So that's congratulations.
That's a picture. Yes, absolutely. Congratulations. I'll be glad to send my book to you, Prayog.
That is well done. Well done. So we will work out the details of that. So again, the book that we're talking about, and we have a slide for it, but just so you can sort of see it straight out, Puzzles to Unravel the Universe by the guest today, Professor Cumrun Vafa from Harvard. It is available all over the place. You should get a copy. It's a wonderful way to introduce yourself to deep ideas of physics through an interactive and a real active, as opposed to just sitting back and letting the author preach to you, which is how most books are. This is one where you can get in on the action and do things, and in that way really gain a intuition for the ideas that Professor Vafa is describing to you. So, Cumrun, thanks so much for joining us for this conversation.
Thank you very much, Brian, for this session. I really enjoyed it, and it's great to connect with your audience. And good luck with all the great work we are doing with connecting science to the wider public.
I appreciate that. Thank you. And we'll be in touch, and no doubt our paths will cross sometime soon. So thanks a lot. See you soon.
Maybe in the cafe somewhere.
Very good. All right, guys. So we're going to now just move into the more ordinary Q&A that we do in these discussions here. I hope I have. I do have. Maybe one of you out there one day is going to send me a pair of glasses. These that I have today are cracked and broken. They're not my wife's glasses, at least. She is using them, but at least now I can see for half a second. So again, sorry for looking ridiculous in one way or another. And yes, Prayog Dash, congratulations on getting the solution. Really well done. And let me just scroll through and just take some general questions. So Ram Say asks, is Allah personified by the Higgs boson? I'm not sure. Maybe this is one that I should have kept Cumrun Vafa on to answer. But, you know, when one uses the phrase God particle when describing the Higgs particle, perhaps it's worth mentioning that, you know, there's a story behind that. The particle physicist and Nobel laureate Leon Lederman, who was instrumental in many of the ideas associated with the Higgs particle, Higgs field, and so forth, people were trying to find the Higgs particle. For instance, at the Fermilab accelerator, where Leon Lederman was associated for many years, and it was very difficult to find the particle. Nobody was finding it. So there was a general joke going around that it was the goddamn particles because it was so goddamn difficult to find this particle. And I think the story goes that when Leon Lederman was going to write his book and call it the goddamn particle, the publisher or the editor or audience surveys, whatever, suggested that the God particle would be a more poetic title than the goddamn particle. So it's just to say that no one is really associating the Higgs particle with any religious tradition, with any real religious outlook. It is, in some people's mind, a more fundamental particle than any other because it endows other particles with mass. Remember how this goes. The Higgs particle is the smallest piece of the Higgs field, and the Higgs field is meant to be a field, a substance, an invisible substance. I like to think of it as an invisible cosmic molasses that fills all of space. And as a particle tries to go through space, it has to plow through the cosmic molasses, and that creates a resistance. And that resistance on the particle's attempt, say, to accelerate is what we call the mass of the particle. So it's a universal mass-giving field, and the universal quality can bring to mind the universal quality of God, if you will. So some people draw the connection in that way, but again, it is just a field of physics like the electromagnetic field like the other fields that we make use of, the gravitational field and so forth. And it's a very special field, but mathematically it's just one more field. So I wouldn't look for any theological connections any deeper than the poetic ones that I just mentioned. Okay, heading onward. Sanjay Pawar, what is dark energy? And again, I think this is a question that we've taken up a few times during these various sessions, but I'm always happy to cover familiar ground. It's important. Dark energy is another kind of field, we believe. It's a field like the Higgs field that does permeate space. It's very related to what I was just describing. But the difference with the dark energy is that the amount of energy density in the field is such that the field has a significant gravitational influence on the universe. The Higgs field does not have a significant gravitational influence. I mean, it does endow particles with mass, so you've got gravity in that story as well. But in terms of the intrinsic source for gravity that the Higgs field is, it's modest, it's minor. Whereas the gravity sourced by dark energy is not modest, it's not minor. It's significant, so significant that we believe it gives rise to the repulsive gravitational push that is driving space to expand ever more rapidly. So it's, again, in some sense, analogous to the Higgs field, but in terms of its impact on the way reality unfolds, it's quite different because of the vast store of energy that yields an important gravitational contribution that yields this accelerated expansion. Now, having said that, let me not leave you the wrong impression. The amount of energy in the dark energy, while enough to yield a gravitational influence that's observable, is still a small amount of energy by everyday standards. I did a calculation, and it's in my latest book. It's a calculation that you can do in the back of an envelope. I could probably do it on the top of my head, but I'll just try to remember the result. If you look at the amount of dark energy in a given cubic meter of space, the energy in there could light a 100-watt light bulb, like the old variety, right? Well, 100-watt doesn't matter, the technology, but I'm having in mind not the 100-watt equivalent of an LED, but actually a 100-watt light bulb. It could keep it illuminated for about 5 trillionths of a second, I believe is the answer. So that's a tiny stretch of time to keep that light bulb illuminated, which is just to say that even though the dark energy has enough energy to yield an observable gravitational influence, the amount of that energy on everyday scales is tiny, absolutely tiny. But that's what that is. So Anas Abu Salham asks, what is dt dx, dt by dx? And that's an interesting question. We all know I hope we all know what dx dt is, right? That's the calculus expression for the change in position divided by the change in time. And the change in position over change in time is speed. That's what we mean by speed. How far you go divided by the duration, the interval that it takes you to travel that distance. What if you flip it upside down and consider dt dx? And dt dx is a number. Well, obviously it's 1 over speed, but you might ask yourself, does that come into physics in an interesting way? And it kind of does, because, and I won't go through it in detail, but there's an analogous version of that, which is d tau dt, where tau is the invariant interval, the invariant space-time interval. So you can talk about d tau dt or dt d tau. And that basically is the rate of change of one clock relative to the clock that's on your wrist. The clock that's on your wrist measures invariant time. It is intrinsic time, if you will. And you can have other clocks that are not moving relative to you. And you can ask yourself, what's the rate of change of your space-time interval compared to their space-time interval? And that is one way of thinking about Einsteinian time dilation and why it holds true. Because in some sense, we are all traveling through space-time at the same invariant speed, which is equal to the speed of light. And if I get up and start to move, I divert some of my motion through time into my motion through space, because I'm now moving through space. I'm not just sitting still. And that notion of moving through space affecting your passage through time, naturally emerges by considering things like dt, d tau, and d tau dt, which is quite related to dt dx. So if you want the details on that, I can send you to a little endnote in my book, The Elegant Universe. I forget which endnote it is, but it's in chapter 2. So you can see how sometimes flipping the calculus expressions upside down can give you important and deep insights. And that's one specific example of that. All right, I've been only looking at the Twitter questions. Let me see if there are any interesting, not Twitter, the YouTube questions. I get my social media sources mixed up. But let's see. John Olson asks, and this is from, I guess this must be from Facebook or Twitter. A black hole question: can two or more massive black holes change the geometry of a small black hole's gravitational field in a way that mass can escape? So it's certainly the case if you've got multiple black holes around, the geometry of space-time at a given point is dependent upon all three of those black holes. So oftentimes when we write down a picture of a black hole, we show a schematic of the geometry, but we show it on its own. We don't show what it would look like if there were a bunch of black holes together with all the various warpings of space-time overlapping in interesting ways. And we can do that. It's harder to do. Sometimes you don't even have exact solutions in these multi-body versions of the general theory of relativity, but you can certainly approximate the solution quite well in many interesting circumstances. And it's not that the new geometry allows the mass of a previous black hole to escape, but it does change, for instance, the trajectories that Hawking radiation, which can escape from any black hole, the trajectories that those particles that are emitted by a black hole will take. So the detailed dynamics in any given circumstance does intimately depend upon the masses and the positions of whatever black holes might be in the environment. And that can affect the ways in which those black holes evaporate. But it does not affect the classical picture that mass can't escape from a black hole itself. All right, so what else do we have here? Shavuk Mandal, again from, and I'll go back to the YouTube feed in a second, but from our social media feeds. How can we verify the predictions given by string theory? We don't understand the quantum behavior fully. How can we look inside a quantum world? It's too bizarre. So a lot of questions in there, but the primary one, how can we verify the predictions given by string theory? Right, that is a question that Cumrun Vafa and I discussed just a little while ago. And as he mentioned, in principle, if you built a sufficiently large accelerator, not one like the Large Hadron Collider that can reach, depending on whatever units you look at, 10 to the 4 times the mass of a proton, that kind of scale. As Cumrun mentioned, you need a detector that's within an accelerator that can reach 10 to the 20 times the mass of a proton. So that's 16 orders of magnitude more powerful than the Large Hadron Collider. Now, where did that number come from? Well, within string theory, a key number is the Planck mass. And the Planck mass is about 10 to the 19, 10 to the 20 times the mass of a proton. And it's at the Planck mass that in conventional string theory, you would expect the extended nature of strings to be visible. So that's why Cumrun mentioned that 10 to the 20 number. And so, right, so if we could build an accelerator with that magnitude of energy, then at least in principle, we would be able to test string theory. So when people say that string theory is untestable, they really should qualify it in a way that they might roll their eyes and say, well, yeah, of course I mean that. But they should qualify it by saying, we can't test string theory right now. But that does not mean that string theory is untestable. And to some, that is a distinction that doesn't matter much. But for those of us within string theory, it's a distinction that really does matter. Because if string theory were permanently untestable, if there were a quality of string theory that said this is fundamentally not testable by any means, then we really wouldn't be doing physics any longer. Some people say, psychoanalysis is fundamentally untestable because regardless of what the patient says, you can interpret it within the rubric, within the framework of Freudian analysis. And in that way, there's effectively nothing that the patient could say that would fall outside that template. But that's not the case with string theory. It's just that we have limited experimental capacities. We advanced human beings here in the 21st century have limited experimental capacities. And string theory is such a bold theory. It is such an ambitious theory that some of its most iconic qualities just don't emerge at everyday energy scales. The theory is so bold and ambitious that some of its key qualities emerge at fantastically larger scales, such as the scales that Cumrun Vafa was mentioning. So how do we test string theory? We may get lucky. Excuse me half a second here. We may get lucky, and one day some clever Einsteinian level string theorist or Einstein squared level of capacity, that person comes along and says, look at this. And they do some fancy mathematical manipulation and out pops some prediction of string theory that we could test with existing technology. And we thought that we might have that with supersymmetry. That's a quality of string theory that might be measurable at energies like that of the Large Hadron Collider, but we've not succeeded. And that might mean that that quality of string theory is wrong. And Cumrun mentioned some of the implications of that. If string theory is fundamentally not realized in a universe that is governed by string theory, that's the big assumption, that string theory is right, but the flavor of string theory relevant, say, to our universe is a flavor that does not involve the supersymmetric quality, at least at accessible energies, that might suggest that the universe is unstable. And it might suggest that, I don't think Cumrun mentioned the number, but it could be that within, a factor of 10, 100, or 1,000 times the current age of the universe, our universe disintegrates. And that is a possibility that I explore in my book and in the book Until the End of Time. The specific version that Cumrun mentioned, as I noted there, is just really an end note, but the possibility that our universe might disintegrate in that time frame is one that we may have to, at some level, accept. But the point for Shavuk Mandal's question is that supersymmetry was one of those qualities that emerges from the mountaintop of string theory and rolls down, and in principle thought might come to rest at energy scales accessible to the Large Hadron Collider. But that seems not to be the case. But there may be other qualities. But if there are no such other qualities, or if we don't have the brain power to extract those other qualities, then the real way to test string theory may be to wait until we have fantastically powerful energetic accelerators or whatever kind of machine takes the place of accelerators in the far future. So it's very much up in the air. Now you can ask yourself, so does that mean that you shouldn't work on string theory? And clearly someone like Cumrun Vafa says that's the wrong reaction. There are the corners of reality that he made reference to, which string theory can illuminate. Now you might say, well, how do we know it's reality? You don't. You don't. But that's what being at the cutting edge of science is. Regardless of what subject you're in, you're pushing into frontiers that you don't know, at least if you're doing theoretical work, whether they're relevant to the real world that we live in. And you take a chance. And some people find it very exciting to take that chance. And they go on into string theory or other speculative fields. There are other scientists that want, hey, I'm working on a project and I want it to be done in 2 or 3 months. And regardless of what the answer is, I want it to be interesting enough to write a paper on it. And there's a lot of science that can be done that way, interesting science. It's just a different way of engaging with reality. So it's all a matter of personal choice. Okay, Deepak Panwar, what is an axion? An axion is a hypothetical particle that naturally emerges from certain attempts to solve famous long-standing problems in particle physics. So there's a problem called the strong CP problem. It afflicts our understanding of the strong nuclear force. C and P have to do with certain symmetries of the mathematical equations, charge conjugation, parity symmetry. And when you look in the strong nuclear force, the equations that we study, there's certain terms that in principle could be there, but they seem to be highly suppressed based on the impact that they would have on experimental predictions that are not observed. And so the question is, how do you argue that these terms should be suppressed? Is there a natural way to suppress them? And it's an interesting long story, but one way of suppressing them is to look at a certain kind of symmetry, a U1 symmetry, for those of you that like mathematical analyses. And associated with that solution is this particle called the axion. And the reason why the axion is spoken of in more recent descriptions of the universe is that it may be a dark matter candidate. It may be the dark matter, is perhaps a better way of saying it. It is a dark matter candidate. And the more traditional candidates that people have thought about for decades, weakly interactive massive particles, or so-called WIMPs, not the nicest of names for these particles, but these particles naturally emerge from supersymmetry, which again may or may not be relevant to low energy physics. But we've searched for these WIMPs and we haven't found them. Or I don't know if that's the best description. There have been moments when we thought we found them, and then the experiments could not make a sufficiently convincing case that the community of physicists had come around to believe that the dark matter had been detected. So just about everybody in physics is of the mindset that we don't know yet what the dark matter is. And with all these experiments looking for one class of particles called WIMPs and not finding them to most people's satisfaction, other candidates have bubbled up to the surface, and this axion particle is one such possibility. So that's what an axion is, and that's why we're interested in them. And we just have to wait and see whether additional information comes around to perhaps convince us that axions are indeed the dark matter. So Diego asks, is symmetry a property of the universe or a property of our understanding of the universe? And that's a variant on the deep question, is mathematics a quality of the universe, or is mathematics simply the language that we humans use to describe the universe? And both questions, Diego's question and my variation on that question, are questions that people argue about all the time, right? I mean, you look out and you see patterns in the world, and in order to encapsulate those patterns in succinct descriptions, one of the things that you do is look for symmetries, right? I mean, a circle is the prototypical example, and a circle is highly symmetric in the sense that if you rotate it through any angle around its center, it looks the same. And because it looks the same, that means you don't have to describe every single point on the circle. If you have described one point on the circle, you've described all points on the circle, because via the symmetry, they all look the same. And that's a very simple example of the power of symmetry, allowing you to reduce the complexity of your description. You can just describe one point on the circle, describe its distance from the center, and you are done. Because every other point is the same distance from the center, and therefore you don't need to talk about them in any explicit manner, and they're all related by a rotational symmetry around the center. Now, is the circle a real thing? Plato had in mind that there was this other meta-universe, or perhaps real universe, where perfect circles lived, and perfect triangles and squares, and all of the perfect versions of the shapes that we describe. They are out there, they're real, but they're in this other parallel reality. Others think about circle as a figment of the human mind. It is something of our own making, that we impose on the external world. And when we find things in the world that look like circles, we impose this pristine version of the circle upon them. And in that way, we model stuff that's out there in the world via these constructs of the human mind, right? So simple example, right? So right here, I got this little bottle top. You know, it looks pretty circular. And if I were to describe it, I'd say the two-dimensional projection of this, I would say it is a circle. But in keeping with Diego's question, we all know that this bottle cap is not really a circle. If you were to zoom in on it, right, I'll get closer and closer and closer. You see that it has rough edges associated with it. If you took an electron microscope in there, and you'd even be able to see the ridges, or you'd even see the atomic constituents that are ragtag arranged in something that approximates a circle, but not a real circle. So that's the question. Are these ideas of symmetries talking about real stuff in the external world, or is it our description of the external world? So if I was to give you my answer, Diego, I would say it's our description of the world. I've come to the viewpoint in recent years that mathematics is a powerful language of human invention for describing things in the world. And within that mathematical language, there are certain idealized qualities. And among those idealized qualities are things that are known as symmetries. Circular symmetry is one, but they're more abstract symmetries that we usually use the mathematical field of Lie groups and Lie algebras to describe those symmetries. And I think that these are powerful tools that we invented to describe the patterns of reality. But to just say that they're actually out there in the world, that's a step that I used to take that I don't take, at least at the moment. So Diego, long answer to a short question, I would say that the symmetry is a property of our understanding of the universe, and that understanding is sufficiently powerful that it can make predictions about things that are out there. So it's not as though it's solipsistic. It's not as though it's all happening in here. We can use that symmetry and that math to make predictions, and the predictions are borne out by experiment. So it's not as though it's all limited to stuff that happens inside of our heads, but I do think that the description is something of our own making. Okay. Local Titans asks, is there a possibility of more fascinating undiscovered behaviors of space-time that might even be more complex than our imagination? And Local Titans, I like that name, Local Titans. I think the answer, of course, I have to say is yes. Is that possible? Yeah. I mean, the history of physics is a history where we're astounded by the concepts that the mathematics forces upon us. I mean, black holes are an absolutely beautiful example. Einstein writes down his general theory of relativity in 1915, a mathematical description of space-time. Within a handful of years, we learn, say, from Carl Schwarzschild, who solves the equations, first one to solve the equations. We learned about this possibility of black holes. They weren't called black holes back in 1917. Rather, they were called dark stars or frozen stars. But this idea that there might be this monstrous structure in the cosmos that sucks in matter that gets too close and doesn't let any of it escape, this ultimate warp in the fabric of space-time, it comes out of the mathematics. It does not come out of imagination. And in fact, it was so shocking that Einstein's imagination couldn't really cope with it. Einstein wrote a handful of papers. I think the last one was 1948, where he was trying to argue that black holes would not be real, that they were just a mathematical figment that emerges from his equations, but not real. But as you all know, I don't have a picture here. I don't know how, if our team can grab a hold of the famous picture of a black hole that was just taken a couple of years ago, right? That's not the only evidence we have for black holes. We had the orbit of stars around the center of our Milky Way galaxy, and we had we had gravitational waves, the particular ripple in the fabric of space-time that we detected back in 2015 the supercomputer simulation showed that it had to emerge from the collision of two black holes. But now we actually have, in some sense, photograph of a black hole. Shep Doleman in the Event Horizon Telescope, they took this famous, there it is. We took this famous photograph, right? So look at the journey from Einstein in 1915 through the imagination of Carl Schwarzschild, 1916, 1917, through the observations of many and culminating with the image that you just saw. So yeah, local titans. I think that pattern will be played out again and again as we go forward. And there will be increasingly strange and weird ideas that don't come from human imagination, that come from the mathematical description of the world. And some of those ideas will be wrong, and some of them will be right, and some of them will be experimentally confirmed, just like the idea of black holes was. So I do think that that is the pattern that we will see persisting going forward. Little doubt on that. Okay, let me go back to our questions here. Nilesh asks, sir, can you please explain Bell's experiment and hidden variables? I can. I'll give you an abbreviated version. It's a beautiful story. It's one that, you know, I'm wondering, have we actually done a full World Science Festival program on Bell's inequality and entanglement? It's certainly been mentioned in many of our programs. It's certainly in a theatrical piece that we are now developing anew on quantum mechanics. It's called Spooky Action, the drama of quantum mechanics. So those of you who liked Light Falls, our theatrical exploration of the general theory of relativity, and those of you who have not seen it, again, I'm not supposed to do this, but I don't care. If you go to this YouTube channel, they should not have it up. It's called the Documentary Channel. I don't know who it is. We didn't put it up because we weren't allowed to. They're not allowed to either, but whatever. So you can watch it on the Documentary Channel. That's a theatrical exploration of the discovery of the general theory of relativity. If you like it, leave a comment there. I always love to see. If you don't like it, don't leave a comment, please. But if you do like it, leave a comment. I love to see those positive comments. But we're developing a version of that kind of presentation for quantum mechanics. But anyway, back to the question. The spookiness in Spooky Action, the title of that piece, is quantum entanglement. And here's the story. Very, very quickly, here's the story. So Einstein himself in 1935, now in the 85th anniversary of that famous paper, Einstein and two colleagues showed that according to the math of quantum mechanics, you could have two very distant particles that behave as though they are one. The canonical example, this is not the example that Einstein used. This is an example that comes from David Bohm, a wonderful character in the unfolding of the history of quantum mechanics. But a given particle can be either spinning up or spinning down. That's the nature of particles. And in Einstein and colleagues' reworking of that idea with this Bohmian version, you can have two distant particles that are both spinning up and spinning down at the same time. They're both in a fuzzy mixture, spinning up and spinning down. And here's the thing, you can go and measure one of those particles and cause it to snap out of the quantum haze. According to the math that Einstein and colleagues showed, the other particle would also snap out of the quantum haze at exactly the same moment, even though you didn't do anything to it. So let me see if I can get in front of the camera here correctly. So up and down the same time, you measure, say, the one in my right hand, boom, snap up. The one in my left hand snaps down. Oh, come on, be in the frame. It's so counterintuitive how to move these things. So it's weird. It's spooky. You do something at one location and it influences a particle at another location. Einstein said, no. There's no such thing as spookiness. He said, but this experiment is really showing you is that these particles that you thought were in a fuzzy mixture of up and down at the same time, they were not. They were always up or always down. And when you measured it and you found it spinning up, it always was up. And the other one, when you measure it and you find it spinning down, it was always down. And if it was always down, then there's no spooky connection. It's not like when you measured the particle in New York, it affected the particle in California because the one in New York was always up. The one in California was always down, period, end of story. No spooky connection between them whatsoever. So who's right? That's the question. Is there spookiness, as the math of quantum mechanics says, in quantum entanglement, or is there no spookiness, as Einstein's interpretation of the experiment would suggest. And many people at the time thought this was not a question that could really be answered. Wolfgang Pauli, I think, described this as a question that was no better than asking how many angels can dance on the head of a pin. It's just not answerable. Why is it not answerable? Because Pauli was saying, look, if you want to know if this particle was spinning up and down simultaneously, and when you measured it, it snapped out of the haze, or if it was always up, and when you measured it, it was just revealing its pre-existing characteristics. Pauli says, how can you ever test that? Because to test it, you've got to measure it. And the point is, once you measure it, it's always spinning up or down. You can never catch it in the act of spinning up and down simultaneously. John Bell, to answer your question, and whose question was this? This is Nailesh's question. John Bell came along and surprisingly found an observational consequence of a particle being in a fuzzy mixture, say, of up and down at the same time. Even if you're not measuring that particle, there's an indirect influence of it being in that fuzzy mixture of up and down that is measurable. You have to be more clever. You can't just brute force measure the particle and say, well, it's up, and therefore I don't know if it was up and down beforehand or if it was just up beforehand. You got to do something more involved, something more clever. And that's what John Bell did. He found a more clever experiment that could give you insight into whether particles have definite features before you measure them, or whether they're in a mixture before you measure them. And to most people's satisfaction, that proposed experiment, which is then carried out, concludes that Einstein was not right on this idea, that particles really can be in this fuzzy mixture, and it only becomes definite upon measurement or observation or interaction of some sort. And to really understand the details in that explanation, you have to really look at it more closely. And in chapter, chapter 4 of Fabric of the Cosmos, I go through, I think it's that chapter, a long time ago now, I go through a very detailed analogy that I believe really captures the heart and soul of John Bell's inequalities and the experimental state of checking those inequalities, yielding the insight that I just described, that at least when it comes to definite properties, Einstein's view seems not to be borne out by the observations. That's one place where you can learn about it non-mathematically, but the math is not hard. So for those of you who are familiar with linear algebra, a little bit of quantum mechanics, you do not need much to really understand the original papers. So I would encourage you to do that. But Nailesh, I hope that gives you the basic idea of John Bell and quantum entanglement. Okay, so just trying to find a good question to take us in a different direction. So Siamak Rajabi asked, can you explain Eric Verlinde's theory versus the general theory of relativity? And again, that's an involved story to describe in detail, but I can give you the flavor for it. So often we talk about general relativity as a fundamental theory of the world. Now, earlier we discussed, what does that really mean? Is it stitched into the fabric of the world, the general theory of relativity, or is it a human description of the stuff that happens out there in the world? And again, I don't know the answer to that question, but a related question is the general theory of relativity a fundamental theory of the world, or might it actually emerge from yet more fundamental considerations? And with Eric Verlinde and others, Ted Jacobson maybe was the first who started along a very similar trajectory, asked themselves, could it be the case that just understanding statistical mechanics, thermodynamics in a gravitational setting might be enough to extract Einstein's equations as opposed to posit Einstein's equations? And these studies have been successful in certain ways. So without even knowing Einstein's equations, but knowing certain very basic features about thermodynamics and certain very basic features of quantum mechanics, these folks have been able to extract aspects of Einstein's general theory of relativity and thereby come to the conclusion that Einstein's theory is an emergent theory, an effective theory, a theory that comes into play in certain contexts, but rests upon more fundamental physical principles. And that's an exciting idea. It's resonant with a lot of things that we think about and discuss and work on in string theory. I mean, Verlinde is a string theorist. I think he would call himself a string theorist at heart. I don't think that is a description that he would consider inaccurate, although much more broad and is thinking about things. But in string theory, there are many who have come to the conclusion, as we began to talk about with Cumrun Vafa in the first hour, that space and time are not fundamental, that they themselves are emergent. That's a spectacularly interesting idea, because every formulation of physics, you go back to anything that Newton wrote down, or anything that Galileo was thinking about, or anything that really happened after, and all of these theories certainly assume a pre-existing spatial environment, a pre-existing notion of time that allows for a dynamism, that allows for things and systems to change over time. You can't talk about change over time without time being part of your description from the get-go. But these newer ideas are suggesting that space and time are not fundamental, that there's a description of reality where when you look at the basic vocabulary, you don't even need to use the word space and time to get the theory off the ground. And then space and time come into play when you apply that theory in certain domains of reality, such as the domains that you and I are inhabiting at the moment. But the space and time and the description that comes from the general theory of relativity of space and time may all be emergent, may all come into play in certain environments, but are not fundamentally part of how the world is put together. That's the basic idea. Andrew Haney asks, will you present a general relativity course on World Science U? And Andrew, I think the answer to that is yes. And just putting all cards on the table, you know that I have this special relativity course. And you may also know, although some of you may not be aware, we just released the video of the non-mathematical version of the special relativity course. It's called Space, Time, and Einstein. We released it just a few weeks ago. We filmed it a while ago, of course. But we took it out of the World Science U universe and put it out just on our YouTube channel. We put it on 2 YouTube channels, actually. The World Science Festival YouTube channel and the World Science U YouTube channel. It's out on both. And yeah, I was surprised. It's gotten a lot of activity, a lot of views. I think between those 2 channels, it's gotten over 300,000 views in the last few weeks. That's fun to see. People are interested. And that sort of motivates me to go ahead and maybe create the general relativity course and also the quantum course. I'm thinking the quantum course I might do first. We're actually building a little studio up here where we are huddled, waiting for this virus to pass. And if we can get that studio built, hopefully it's in the next month, ideally, one of the projects that we'll do in there is to film a quantum course for World Science U, analogous to the special relativity course that already exists and the general relativity course. So I will give you a tentative yes, Andrew. I don't know the time scale for the general relativity course, but I'm going to go out on a bit of a limb here, and I'm going to try to get the quantum course done by like December, January, something like that. And again, I'm going to try to do a non-math version that's embedded in the math version, so that those of you who don't like the math can take the non-math version. And if you feel motivated, you can then watch some of the surrounding material and see the mathematics behind some of these ideas. So that's certainly a project that is moving from the back burner, heading toward the front burner. So we'll see how that affects things going forward. So Amjad asks, can the Casimir effect describe gravity at the quantum level? And that's a very interesting idea, Amjad, because the Casimir effect, I think, I hope, well, maybe I should say what that is. I don't know if I don't have any show and tell with me, so I just have to use my hands. But if you take two metal plates and you bring them very, very, very close together, there's an interesting force that comes into play. If these plates, I mean, forget about gravity just for the moment. If these plates have no electric charge, you wouldn't expect there to be any force between them. It doesn't matter how close together, how far apart. If they're neutral objects and you're forgetting about gravity, then there's no other force that would act. But quantum mechanically, there is a force, and it has to do with the undulations of the fundamental fields like the electromagnetic field, because the quantum undulations of the field outside the plate is fundamentally different from the quantum undulations that quantum mechanics allows inside the plates. And that difference creates an imbalance that in certain circumstances can force the plates to come together, or in other geometries can force the plates to push apart. And that force is called the Casimir force, the Casimir effect. And the beauty of it is it's measurable. Casimir did these experiments in 1948. Dutch physicist, I'm pretty sure it was Dutch physicist, did these experiments in 1948. So it was measuring the difference between the quantum undulations in the vacuum between the plates versus exterior to the plates. And so it's this beautiful macroscopic way of testing quantum effects. Can you use those ideas to test gravitational effects? And the answer is definitely yes. The question is it detectable? And there's a beautiful relevant paper to these ideas that I just was reading by Nobel laureate Frank Wilczek and an old friend of mine. I guess I can call him an old postdoc of mine, actually, named Malik Parekh, who is now in Arizona. Is it Arizona State University or University of Arizona? I get those mixed up. I think it's Arizona State University. And they've written an interesting paper trying to see whether, quantum effects analogous to the Casimir effect, really, that come into play when you measure gravitational waves. Could those subtle quantum effects be used to perhaps gain insight or detect gravitons themselves? Gravitons are the quantum of the gravitational field. Photons are the quantum of the electromagnetic field, right? You're seeing me right now because photons are emanating from your screen, traveling, banging into your eye, hitting your retina, causing a cascade of other particle interactions inside your eye, sending a signal down your optic nerve to your brain. That's how you are seeing me. It's all coming from the seed of photons interacting with your eye. Gravitons do for gravity what photons do for the electromagnetic field. So there's a debate among some physicists as to whether gravitons are actually real. This is where that remark I mentioned in the first hour when I was talking to Cumrun Vafa, that Freeman Dyson seemed to not think that gravitons are real. But if they are real, then what Wilczek and Malik Parekh have suggested is that these kind of gravitational wave-like technologies, properly used and interpreted, might give us insight into the nature of gravitons or even the reality of gravitons. So yes, in principle, the answer to that question is yes. Sanjay says, I'm like team physicist young Sheldon. Thanks for sharing, Sanjay. I'm not sure how to respond to that, but I guess that's a good thing. So I will leave that. I will leave that at that. Anas asks, what's the natural log of a matrix? And so that's a slightly technical question. But what we do in physics or mathematics more generally, when you want to talk about operations on a matrix, the operations that we know easily for matrices, we know how to add matrices, we know how to multiply matrices. Those are the easy things to do. And so what we do is when we look at more complicated functions of a matrix, where like with a natural log, you don't really know what to do when you apply that to a matrix, we do know how to create a series expansion that approximates the function that you might be talking about. For instance, for an exponential, which is the inverse of the natural log. Well, how do you exponentiate a matrix? Well, we know how to have a series expansion for an exponential. E to the x It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That's the series expansion for an exponential. If you were to now put a matrix up there in the exponent for an exponential, you'd say, what is e to a matrix? I don't know. But if you plug that matrix into the series expansion, you do know what it is. 1 becomes the identity matrix. X is just the matrix itself, plus x squared over 2. You know how to square a matrix. Square a matrix, you multiply it by itself, and so on. So if you have a series expansion, then you can use that as the definition of that function of a matrix. And you do have a series expansion within limits for the natural logarithm. And that's how you define the log of a matrix. So thanks for that question. Hope that wasn't too technical. But that is how typically people interpret the natural log of a matrix. Mr. Space asks, hello, Mr. Greene. If space is expanding everywhere, does this mean that at the nanoscale, or even smaller, that the distance between atoms is also expanding? And the answer to that question is yes and no. What do I mean by that? Well, when you talk about space expanding on large scales, you're talking about scales that are so large that the gravitational influence between entities within space is so small that the attraction between them is not influenced by gravity or, in fact, any of the other forces of nature. And therefore, you just focus upon the movement that comes from the dynamics of spatial expansion itself. And indeed, that can drive distant galaxies to move away from each other. When you talk about the same ideas on small scales, like nanoscales, or you don't have to go that small, talk about these scales, right? Are the atoms in my broken glasses, are they moving apart from each other because of the expansion of space? And generally we say no. Why do we say no? We say, no, God, my glasses are so dirty, it's kind of gross. We say no. I'm going to clean my glasses as I'm answering the question. We say no because my glasses are held together by the electromagnetic force. Not strong enough to hold this arm on. The electromagnetic force was overwhelmed there by like my dog's teeth or something sitting on my glasses, caused it to crack. But the atoms in my lenses, they're held together by the electromagnetic force, which is stronger than the outward swelling of space. And that's why the atoms in here are not moving apart in the way that you suggest, Mr. Space. But if the expansion of space were to get stronger, and that's possible, if the expansion of space is not only speeding up, but the rate of speed up is speeding up, then it's possible that in the future, the outward swelling of space is so powerful that it would cause the atoms in the lens to move apart, shattering my glasses. And it would indeed cause the electron orbiting the nucleus of an atom to expand away from the nucleus, causing the atom to disintegrate. And if that were the case, then that kind of expansion would destroy everything. So as of today, the answer to your question, Mr. Space, is no. Atoms are not being driven apart by the swelling of space. But in the future, if the expansion picks up in its ferocity, then individual atoms could be moved apart from each other, and even electrons within atoms could be driven apart from the nucleus, causing everything to fall apart. That is a potential future that we potentially face. Okay, so what else? I'm going to go back to my other list of questions that comes in from social media things. Anything fun there? Let's see. So Kapil Sharma asked a question just like Mr. Space, but I'm not going to answer it again, but very close. So Nomad asks, in inflation or cosmology more general, we imagine that the Earth is 13.8 billion light years away from the Big Bang. I'm not sure I would exactly say it that way, so I'll come back to that in a second. And that means that the age of the universe for us is 13.8 billion years. I'll buy that. What about celestial bodies that are farther away and can't be seen by us? So a number of questions in there, Nomad, which is your full name. So I wouldn't say that we're 13.8 billion years 13.8 billion light years away from where the Big Bang took place. I would not say that. I understand what you mean by that. What you mean by that is if we were to see the Big Bang, like, let's be concrete. When we look at the cosmic microwave background radiation, which was released just, a few hundred years after the Big Bang, those photons have been traveling toward us for on the order of 13.8 billion years. So they emanated from a point in space that is 13.8 billion light years away, at least when that photon left at that point in space. So what does that mean when we talk about a photon that's been traveling through space for so long? And I just realized what I just said was a little bit wrong, so I should really clarify that. So when we see something in space, we are seeing it, of course, as it was a long, long time ago. And when we say that the universe is 13.8 billion years old, what we mean is that the Big Bang happened that long ago, and therefore, were we to actually see that event, you'd be seeing an event that happened far away in the distant past. But you see, I wouldn't say that the Big Bang happened at a distant location. What I would say is all locations that are now separated were on top of each other at the moment of the Big Bang. So the Big Bang happened where you are, where I am, where everything is located, because all those locations that are now distinct were the same location. So clarification number one, I would not say that the Big Bang happened 13.8 light years away from us. There was a bang that happened there, but we don't need to distinguish that bang from our bang because those locations were the same location. But in terms of the second question, in terms of celestial bodies that are even further away that we can't see, yeah, we make a very sharp distinction in physics between the universe and the observable universe. And the celestial bodies that we can't see, nomad, are in the universe, but they're not in the observable universe. And so we make assumptions about what those celestial bodies might be like. We generally assume that they're pretty much like what we recognize by close examination of things in the observable universe. But that could be wrong. It could be that the observable universe is completely misleading. It suggests that there are stars, galaxies, and planets and things of that sort. And we imagine that well beyond that, there are stars, galaxies, planets, and things of that sort. But it could be that beyond the observable universe, I don't know, maybe there's nothing. Maybe there's all sorts of other stuff that we've never even thought of. That's quite possible. Since we can't see it yet, or perhaps ever, depending upon how the universe expands, it's difficult for us to say anything. Our theories are well commensurate with this assumption of homogeneity, that what we see here is a good guide to what we see out there. Just like, you look at one little chunk of a circle, even if you weren't looking at the rest of it, if you know it's a circle, as we discussed before, that one chunk gives you a lot of information about other chunks on the circle. We're looking at one chunk of the universe right now. Does it give us insight into other chunks that may be, as Nomad asks, too far away for us to see? And we don't know. The inflationary theory allows for on incredibly large distances for the universe to be quite different. It allows for us to be part of a multiverse where those other universes might have radically different properties from the properties of our universe. So the homogeneity might be a local homogeneity that sort of works in our environment. But if you go into other environments that emerge from other universes, that come from other bangs in the inflationary theory, the physics and properties of those universes might be quite different. And that's an exciting idea, and one that has been harnessed in string theory to give answers to questions like, why does the dark energy have the particular value in our universe that it does? We've not been able to answer that question through a straightforward first principles calculation in our universe. So what have some people suggested? Well, they suggest, hey, what if there are other universes, as Nomad notes? And what if, as Nomad's question suggests, those other universes have quite different properties? And in particular, what if those other universes have different amounts of dark energy. And moreover, what if the spectrum of possible amounts of dark energy out there in this multiverse varies enormously, such that, in effect, every possible value of the dark energy is realized in some universe that's out there? Now, in that totality of universes, that would mean that every possible value of the dark energy is realized, which means that the value that we have doesn't need explanation. It's just one value of the spectrum of all possible values that are out there. And therefore, it had to be that there was one universe with our particular value. And here we are living in that universe. The analogy that I like to use, it's imperfect. But, you know, if you go to a suit shop, you're looking for a dinner suit, and they pull one off the rack and it fits. Should you be surprised that they had a dinner jacket that fit you? Well, if they had only one size, then that would be incredibly lucky and you should be surprised. But most stores don't have just one size. They have all possible sizes, within reason. They don't have a continuum of sizes. They have all possible discrete sizes between some small and large. And within that spectrum of possibilities, of course, there's going to be one that pretty much fits you because they've got all possible suit sizes on the rack. So in a realm that had one size, surprise. In a store that has one size, you should be surprised. In a store that has all sizes, you should not be surprised that one fits you. Now take that idea to the universe. If there's a multiverse, then all possible sizes are out there. So you shouldn't be surprised that our size, by which I mean our amount of dark energy, is out there. If the universe was not a multiverse, if we were more like that suit shop that had one size suit, then yeah, we should be surprised by the particular value of the dark energy that we've measured. It's some strange number that we don't have any insight into. But here's where Nomad's question helps us out. If the other universes exist, and if they've got different values for the dark energy, we're just one of the collection. And that's a potential solution to the amount of dark energy in our world. The solution is you don't need to worry about it. We're just one of the complete collection that is out there. All right, back to questions on our YouTube feed here. Rob Vandenberg asks, where do you stand on the existence of karma or luck? Well, what I would say is we like to use that language and we like to impose those concepts. And those concepts, as high-level human ideas, for some are useful. Some like to think, hey, I do good to the world, and that is good for my karma, and some good will come to me. And when that good comes, people in this way of thinking about things say, yeah, they're like, oh yeah, that confirmed it. I did that nice thing last year, and now this nice thing happens to me. And there's a certain kind of coherence and explanatory satisfaction that comes from that way of looking at things. If you view karma and luck in that light as higher level human ideas that some people find useful and satisfying and gratifying, then I think that's a fine kind of structure to give coherence to experience. But fundamentally, do I believe that there truly is something called karma? Do I fundamentally believe that collections of particles come together and do something good today because collections of particles came together and did something that we humans consider good yesterday? No, I don't. I think the particles that make up matter, that make up us, that make up our brains, are doing what they do because of the laws of physics, not because of some higher level conceptual framework of luck or karma. Those ideas are what we humans employ to try to make sense of experience. And in that regard, they can definitely play a role of helping people make sense of experience. But fundamentally, no, there's no such thing as karma that you'll find in the fundamental laws of physics. There's no such thing as luck that you'll find in the fundamental laws of physics. particles do what they do because they are following the fundamental laws. Now, whether we have those laws or not, I don't know. I've said this before. It could be that we have those laws, or it could be that we don't. It could be that we have a mere approximation to deeper laws that will be revealed through experiment and observation and research over the next 10, 20, 100,000, 10,000 years. I don't know how long it's going to take. But I have confidence that in whatever laws we come up with, whatever laws our future brethren come up with, I do not believe that fundamentally within the laws there will be anything that we can identify as karma or luck or consciousness or good or evil or wonder or love or surprise or anxiety or any of the qualities that are vital to understanding ourselves as human beings, navigating the reality that we are within. Rather, these higher level concepts are manufactured by the human brain, or other brains may manufacture them too, or other ideas may come from other brains. But the point is, these concepts are manufactured certainly by human beings because they're useful when human beings come together in communities and want to have an effective and efficient way of navigating the environment and surviving. And so these ideas are powerful, they're useful, but they are not fundamental in the same way that Einstein's equations or Schrodinger's equations are fundamental. They're just different. Yash Bakshi asks, are you vegan? Yes, I am vegan. I'll leave that at that. Follow up if you'd like. Strumento asks, can we upload our brain? Well, certainly not today. We cannot upload our brains. Obviously, in many sci-fi scenarios, people have imagined that you might be able to upload your brain. And I don't see any fundamental reason why we couldn't. Now, look, there's a big assumption in there. I'm assuming that our brains and our thoughts and our consciousness and our sense of self, our personal ability to conjure inner worlds of self-reflective experience, I believe that all of that is nothing but the motion of particles coursing through a particular structure that is the template within which those processes happen and the substrate within which those experiences take place. Not everybody agrees with that, right? I mean, there are some who suggest that consciousness is out there. There's kind of like a consciousness field that we tap into. I don't see any evidence for that. Can't prove it wrong, but I do base my views on reality on the things that we have confirmed through observation and experiment. And so focusing upon the things that we've established with experiment and observation, it leads me to the materialist, physicalist view that I just articulated. Now, if that's the case, if the physicalist stance is correct, then in order to upload my brain or yours, we just need to replicate the physical structure, and we need to replicate the physical processes taking place in that physical structure. So if you're able to do that, then I don't see any reason why the resulting artificial manufactured structure would not think and feel exactly, say, as I do if it was modeled upon my brain at this particular moment. And similarly for your brain. Can we do that? No, it's hard. Will we be able to do that one day? I don't see any fundamental obstacle, but whether we'll gain the expertise to do that with adequate fidelity to really reproduce the brain that's inside your head and my head right now, I don't know. But fundamentally, I don't think the laws of physics as we understand them stand in the way of that. So Gulab asks, what are time and space, and can string theory answer this at a deeper level? So I don't know, Gulab, if you were with us in the first hour where we had a conversation with string theorist Cumrun Vafa, and that was one of the things that we discussed. And as Cumrun was saying, you know, there are a lot of insights into the nature of space and time that are coming from string theory. One of the most striking is one that we're going to do a full World Science Festival program on in the coming weeks. It has to do with quantum entanglement, which is the answer to an earlier question on the nature of Bell's inequalities that I described before. But quantum entanglement suggests that the threads stitching the fabric of space may actually be the threads of quantum entanglement that in some sense connect distant particles in the manner that I described before. So that would suggest that we are heading toward a deeper understanding of space and time because we're beginning to identify the threads that stitch them. But as Cumrun Vafa described, descriptions of space and time in one domain, in one theoretical framework, can be distinct from and even contradict the descriptions coming from other corners of the illuminated landscape of string theory. So it's not to say that we have an answer, the answer for what space and time are. Much as Cumrun said, it may be that the best we'll ever be able to do is say, in this and this circumstance, according to this and this way of describing that circumstance mathematically, here is how you should think about space and time. And then in the same or subsequent breath, we may say, but in this circumstance, according to this theoretical framework, using this mathematical articulation, this is the way you should talk about space and time. And it may not be that one of those is right and the other is wrong. It may be that both are right. It may be that both are right and complementary. And maybe the fullest story comes from this mosaic, this amalgam of distinct descriptions. And it's only by taking in the full mosaic that we'll have the deepest and fullest understanding of what space and time are. Okay, I'm going to head back here to your YouTube questions. So I know that a lot of you are watching on different channels. I'm focused right now on the World Science YouTube. I probably should have said that. Those of you who are watching on the World Science Festival YouTube, it's very confusing, isn't it? We have a lot of properties out there. So in the World Science Festival YouTube, that's where I am right now. Ask any questions that you want. If you're on the World Science YouTube, I'm not looking at those. I can't look at multiple feeds, but maybe someone on our team will pick out some questions there and add it to my alternate feed coming from the social channels. So it's up to you where you're looking at this, but I am focusing on the World Science Festival YouTube feed. And given that, what do we have here? Okay. So Daryl Dawkins asks, how is it possible to express the age of the universe using years, since years refer to the Earth going around the sun? How are the years calculated before a star even existed? Yeah, good question, right? So we talk about 13.8 billion years. What does that mean if you're talking about a measure that's tightly tied to the motion of the Earth around the sun, and the Earth's only been going around the sun for the last 5 billion years? So what we do, Daryl, is we use the duration of year as defined by the duration it takes right now in the common era for the Earth to go on a full orbit around the sun. We use that duration as our fundamental scale of time. And then we use our mathematical equations to work out the duration back to the Big Bang. And we express that duration in terms of how many times an Earth would have had to go around the sun at the speed that it currently does. And in that way, we express the duration back to the Big Bang in this particular unit called the year. We're not literally imagining that there were 13.8 billion orbits of the Earth around the sun since the Big Bang, because as you rightly point out, for instance, at the moment of the Big Bang, the Earth didn't exist, the sun didn't exist. Rather, we're being a little bit more abstract than that. We're imagining the Earth going around the sun as just providing us a definition of a standard duration called the year. And then relative to that standard duration, we calculate the time back to the Big Bang and calculate how many times the Earth would have had to go around the sun to exhaust the duration back to the Big Bang. And that's where the 13.8 billion years comes from. And, there's a related question to that, which is, we learn from special relativity that time varies depending upon your motion. And in the general theory of relativity, we learn that time varies depending upon the gravitational field that you are experiencing. So when we talk about 13.8 billion years, what do we really mean by that? Which clock are we using? Are we using a clock that is in motion and therefore would differ from other clocks and so on? And the answer is, going back to the question before, we imagine that the universe is homogeneous and isotropic, which means that it looks the same in more or less every direction if you average things out, and every chunk of the universe that's sufficiently large on average looks like every chunk of the universe. And because of that uniformity, we imagine that we have clocks that are experiencing that average motion of expansion, that average gravitational influence of the things in the environment. And because the averages are the same everywhere, every clock is experiencing the same relativistic effects, and therefore every clock is ticking off time at the same rate. So using those universal clocks that are experiencing the average density and the average expansion motion of space, we are calculating that the duration back to the Big Bang would be 13.8 billion years. That's what we mean by that. All right, a few more. What time is it now? We've been going about 2.5 hours, so I'm going to probably wrap this up relatively soon, as I am starving. And thanks for coming at this different time, by the way. So, as I mentioned last time that we met, I have to teach at our old time of 2 p.m. Eastern Standard Time. So this will be our new time going forward, I think. Oh, who knows? Maybe we'll move it around and get people in different time zones. I don't know if that'll be more confusing than it's worth, but we'll see. So a few more questions, though. Arnav asks, where do you teach? I teach at Columbia University in Manhattan. And it was just announced that Columbia University is going to be fully online for the undergraduate education. So I will be teaching fully online. So in principle, yeah, no matter where you are, you could take my classes. I don't think it works that way, though. If Columbia gave every class away like that, they might have, I don't know, trouble attracting students to pay tuition, especially if students are not coming to campus. Wow. Difficult, interesting questions that people need to deal with in this era. But yeah, so I do teach at Columbia University, and I'm actually teaching a course. I'm not teaching a technical course, so maybe you guys wouldn't even be interested. I am teaching a course on my new book, on the book Until the End of Time. And I do take the students right from the beginning of time to the end of time. And there's a bright spotlight that we shine on the emergence of life, the emergence of mind. And that spotlight continues to illuminate what conscious minds do. They develop language, they tell stories, they develop myths, they develop religions, they engage in artistic and creative expression, and they develop science to try to be able to tell the most accurate story of the objective physical reality that allows for all of these life-like activities to take place. So that's what the course is about, sort of a blending of science and the humanities. And yeah, maybe you guys, if you're interested, some of you can audit that course. I don't know how that works, so I can't promise that. But sure, that's what I'll be teaching starting in a week or two. All right, what do we have here? Time Traveler asks, who first came up with the idea of string theory and how? The very initial ideas of string theory, I think, are usually credited to the work of a very nice physicist, friend of mine, known him for decades, Gabriele Veneziano. And as the story goes, Gabriele Veneziano was trying to understand experimental data in the 1970s, or even 1960s, I'm sorry, yeah, having to do with the strong nuclear force, and noticed a pattern in the data of the interactions of strongly interacting particles that could be described by a particular interesting formula that he wrote down, and others, I guess, may have written down too. And when other physicists began to study this formula that was very good at describing the data of the strong nuclear reactions, they studied this formula, and this is people like Leonard Susskind and people like, I think, Holger Nielsen and others at the time. They began to see that in the mathematical description of the nuclear force, you could see vibrating filaments in the mathematics, or the qualities of vibrating filaments were embedded in the mathematical description. And this began to lead people to think about a theory based on strings. And it's interesting because the data that Gabriele Veneziano was trying to describe was subsequently, I don't know what's wrong with my speech at the moment. I guess 2.5 hours in, I begin to get dry mouth. So hang on, have a second here. The data, that's better. The data that Gabriele Veneziano was looking at was subsequently described by a completely different theory, the theory of quantum chromodynamics. So the motivation for the formula that Veneziano wrote down was undercut by these subsequent developments in quantum chromodynamics, but nevertheless, the formula had already been written down. And the conclusion that that formula described vibrating strings had already been met, or made is perhaps a better word. And so string theory carried on even after the motivation to describe the nuclear reactions evaporated. And that mathematical endeavor ultimately revealed a vibrating string that had the properties of the graviton. The hypothetical graviton, you could see that right inside the vibrating filaments, which themselves were right inside the formula that Veneziano wrote down. And with that, people started to think, wait, if you got a graviton, this must be a theory not of just the nuclear force, but of the gravitational force. And that's where the development of string theory as a quantum theory of gravity really took off. Excuse me. Okay. A few more questions and then we will call it quits for today. So Anas asks, does the Ramanujan summation have real life implications? And I guess it depends on what you mean by real life. But a lot of the insights of Ramanujan have had a role, say, in string theory. String theory of real life? I don't know. But certainly the idea of the number of dimensions in string theory, the ideas associated with certain mathematical formulations make use of modular forms whose properties go back to insights of Ramanujan. So I would say that a good deal of the mathematical framework of string theory has an intellectual root that trellises back. It's probably the wrong verb there. Intellectual root that kind of digs its way back to the insights of Ramanujan. So that's a very interesting and exciting link between abstract mathematical ideas and those of cutting-edge physics. Okay. Abhishek asks, can more than two black holes merge to form a single black hole? And absolutely. So if you have a collection of black holes that come together, ultimately when they come together, they will shake the fabric of space. But as those merging black holes ring down, as the fabric of space carries away enough energy from that collision, they will coalesce into a single big black hole. So yes, although we often describe the merger as a binary operation between two black holes, in principle, it doesn't need to be that. It could be sequential, right? Two black holes come together, yield one, and then a third black hole joins with those to create an even larger black hole. Or it's unlikely, but it's conceivable for three black holes to just come together. In principle, there's nothing that would prevent that from happening. Lahanash asks, can quantum entanglement be used to transfer information faster than the speed of light? And I think most of us believe that the answer to that question is no. And I understand exactly where that question is coming from, because as I described before, if you have these two distant entangled particles that are kind of in this state of entanglement where, say, one is up and one is down, you measure one, the other pops out and spins down. That, according to the math of quantum mechanics, is an instantaneous process. So you measure the particle in New York, you find it up at the same moment the particle in California spins down. It feels like there is an instantaneous transfer of information, but actually there's no information to be extracted whatsoever. And the reason is because, look, in New York, let's say you do this experiment over and over and over again, and you look at your data. What will your data be? Well, you go and you measure the electron in New York spinning up on the first run, and then you measure it and it's spinning down on the second one. And you measure it on the third one, spinning down on the third one, and then spinning up on the fourth one. So you have a random sequence of ups and downs in New York. If you look at the data in California, it will also be a random sequence of ups and downs, with the only interesting fact being that when this one in New York is up, this one in California is down. When this one in New York is down, this one in California is up. Now, that's an interesting correlation between the data, but you can only recognize that correlation when you bring the two data sets together. You get on the phone and you talk to the person at the distant location. You say, hey, my data was up, up, down, down. What was your data? They say, hey, mine was down, down, up, up. You're like, whoa, complete correlation. When yours is up, mine's down, and vice versa. Or you could take your data set and you got on an airplane and you fly to the other side of the country and you compare your data set in person. My point, though, is you have to do that comparison in order for you to extract anything informationally interesting about the data. But that comparison is through an ordinary, classical, slower than light channel. So the only time you extract anything informationally interesting about these two data sets is through that slower than light comparison. And that's why there's no faster than light information that's being transferred or can be extracted from quantum entanglement. Okay, I think, guys, I'm going to wrap it up today. I am still getting my ability to go 3 full hours back into shape, right? I have to sort of exercise more to do that. So thanks for joining us today. And I don't know when our next session is. It's either next Friday or the Friday after, sort of play it by ear. Some of these times we'll have a guest, as we did today. And many of you thought that was interesting last time. And let me know if you thought it was interesting and useful today. I had a good time speaking with Cumrun Vafa about his book. And next time we'll venture forth into, again, whatever directions you'd like to go. I love to hear from you guys through social media. Again, I'm B Greene on Twitter. I'm B Greene at Facebook. I think I'm B Greene too, but I haven't used it in a while, so I have to figure that out. You should subscribe. I don't know where the subscribe button is. It's like somewhere at the bottom of the screens here. I'm not going to try to use. Is there a subscribe button? I don't know. I hope there's a subscribe button down there. But if there is a subscribe button, do join in, because then you'll be alerted when these sessions and other programs are happening. And keep abreast of what we're doing. We're going to have some new courses coming out on World Science U. We're going to talk to many of the faculty on World Science U, whose courses we will be releasing. And I'm always here to answer any of the questions that come to your mind, be they in quantum mechanics, cosmology, general relativity, basic physics, string theory. As you see, I'm happy to talk about certain aspects of philosophy, religion, consciousness, mind, brain. If you find what I say interesting, fantastic. If you don't, that's fantastic too. But I hope that you do. And until next time, then, keep your interest going, keep the questions coming. And I look forward to having our conversation either next week or the week after. Until then, take care.